Hello, I'm Dr. Jonathan Rhoad, and I'm going to be showing you some chemical demonstrations today where we get to learn a little bit about some fun things that we can do with chemistry. One of the most important things that we can know about water is how acidic or how basic it is. Chemists refer to this measurement as its pH. So the pH of a water is something that we can measure in many different ways. So one way that is very useful for us to measurement is by using an indicator. So here I have some water, and I'm going to put in a little bit of indicator, and the indicator helps us see something about what the pH, or that acidity or basicity, of a solution is. So I'm going to make this solution just a little bit basic. There we go. I've turned our solution basic, and so now it is a blue color. I made it more basic by putting in sodium hydroxide. But now I'd like to reverse that process. I'm going to take this solution and make it acidic again. And I'm going to do that by just saying yellow into the flask. Maybe you can see there we're already getting a little bit of a change in the color of the solution. It's gone from blue to green, now to kind of a yellowish green. And now we've got a yellow solution. The chemistry behind this transformation is pretty straightforward. Whenever I breathe out, I'm breathing out carbon dioxide. When carbon dioxide dissolves into water, it becomes an acid. So just by breathing into water, we can take it from a basic solution that was shown by the blue color of our universal indicator, and then we can lower its pH, we can make it more acidic until we get to this yellowish solution. Watching the pH change as we breathed into that bottle was pretty cool, but I think there's some cooler things we can do if we're going to play around with pH. So once again, I have some water. This time this water is mildly acidic, and so it is red. So let's go ahead and pour some of that into our container here. And so what we're going to do is we're going to play with our pH by having this red liquid, right, that's already acidic, and then we're going to add some base to it, but we're not going to completely mix it up. And let's see if we can get a pretty cool result. As you can see, we've got some pretty cool colors here. We've got purple down at the bottom, and then blue, kind of a thin layers of green, yellow, orange, and then up at the top, we've got our red. That's our pH rainbow. The progenitor of chemistry was a discipline known as alchemy. The primary goal of alchemists was to do transformations. Modern chemists like to do transformations as well. And so one of the key transformations that an alchemist strove to do was to change base metals, like this penny, into more precious metals like silver or gold. And so he would take his copper and he would place it into the alchemical solution. And he would say his magic words, his incantations, to cause the transformation to take place. And moments later, he would be able to draw out, instead of a copper penny, a silver penny. But silver wasn't good enough for the alchemist. They would use the element of fire to turn it into gold.
Rather than that base copper penny, now what they see is a golden penny.
But we all know that it's not possible to turn copper into gold. If it were, gold would no longer be precious, right? No one would be yearning after gold if you could just make it out of copper by putting it into a simple solution and then heating it. So I'm going to try this again, get a little more on there. What we're actually doing is plating a little bit of zinc onto the surface of our penny. Zinc is the same color as silver, so most people would be none the wiser. And so then once a sufficient amount of zinc is plated onto the surface, right, using this simple chemical reaction, we can plate the zinc onto the surface, rinse those excess chemicals off. Right, so now we've got, once again, a penny that looks very silver. So we're going to heat it. What we're actually doing when we heat the penny is we're forming it in alloy. So we're actually heating up those copper atoms and the zinc atoms enough that they're blending with each other, and we're making a solution, right? Chemists are real big on solutions. So in this case, our solution is a mixture of zinc atoms and copper atoms. And that particular mixture is referred to as brass. So I haven't actually made gold pennies. What I've actually made are brass pennies.
So you can see the apparent transformation from a copper penny to a gold penny, which is really a brass penny.
So if you've ever seen somebody in a movie or a cartoon, whenever they get gold, they bite into it. There are a couple of reasons they're doing that. One, gold's actually pretty soft, really pure gold. You can kind of sink your teeth into. Another is if somebody's pulled this trick. If you just have plated a little bit of gold onto the surface of something that's less valuable, or plated a little bit of brass onto the surface of it, then you'd be able to scratch that off and see the baser metal underneath. We here in the Missouri Western Chemistry Department love doing demonstrations, and one of the biggest days of the year, one of our favorite days of the year, is Super Science Saturday. And what would a Super Science Saturday demonstration be without a demonstration of super saturation? A solution is a mixture of two substances that evenly distributes those two substances throughout so that you can no longer tell the difference between them. So for example, if you had some salt water, right, that is a solution. So what I have here is similar to that. So this is a solution of sodium acetate in water, or you might say it's a solution of water in sodium acetate. So when you look at this solution, you might think, well, there's more water in there than there is solid. And so there's a good way for us to test that out. What we've actually done is dissolved far more sodium acetate than should be able to dissolve in the water in there. So we've mixed those two together, and so we've made a solution that's referred to as super saturated. So when you have a super saturated solution, it's possible, if you give it a pattern, to go crystals out of that solution.
We here in the Missouri Western Chemistry Department love doing demonstrations, and one of the biggest days of the year, one of our favorite days of the year, is Super Science Saturday. And what would a Super Science Saturday demonstration be without a demonstration of super saturation? A solution is a mixture of two substances that evenly distributes those two substances throughout so that you can no longer tell the difference between them. So for example, if you had some salt water, right, that is a solution. So what I have here is similar to that. So this is a solution of sodium acetate in water, or you might say it's a solution of water in sodium acetate. So when you look at this solution, you might think, well, there's more water in there than there is solid. And so there's a good way for us to test that out. What we've actually done is dissolved far more sodium acetate than should be able to dissolve in the water in there. So we've mixed those two together, and so we've made a solution that's referred to as super saturated. So when you have a super saturated solution, it's possible, if you give it a pattern, to go crystals out of that solution. So as you can see, as I pour this solution out, I put it onto crystals that were already in the tray that gave the pattern to the sodium acetate to form more crystals. So as I poured it out, you can see there's actually a very tiny amount of water, and the vast majority of what I have in the tray now is the solid sodium acetate.
Chemists often get really excited about chemistry, and when we get the most excited, when our molecules get excited with us. There are several different ways that you can excite molecules, and also different ways that you can tell that they're excited. One of our favorite ways, I'm just going to go ahead and speak for all chemists, one of our favorite ways is when the molecules shine light back at us. So there are a few different ways that can happen. Things like fluorescence, or phosphorescence, or chemiluminescence, right? So those are the special words that chemists use to describe the different ways that molecules can shine out light. So first I'm going to show you some molecules that are fluorescing.
To make a molecule fluoresce, it's pretty simple. We're just going to shine some ultraviolet light into the molecule. So there you can see, whenever I shine ultraviolet light, right, if I shine it on my hand, you can't really see anything. But when I shine it on these chemicals, you can see a faint glowing of red there, right? So what's happening is the ultraviolet light is going into those molecules, exciting them, and then they're glowing very faintly red. And so I have a different compound here that will glow blue. And so that one's actually glowing a little bit better. You can see this one better if I shine the ultraviolet light through this way. We can see that blue glow.
So fluorescence is pretty cool. What we saw before, when you shine the ultraviolet light into the compounds, that makes those things glow. Whenever we shine the ultraviolet light into the compounds, it makes them glow, but really short amount of time, right? So it's only while we're shining the light on them. And as soon as we turn the light off, then that fluorescence goes away. So an even cooler thing to do would be to make maybe a mixture that just glows on its own. We call that chemiluminescence. Chemiluminescence is a chemical reaction that causes luminescence, right? So this is the reaction that's going on inside glow sticks.
So what we're going to do is we're going to use some very concentrated hydrogen peroxide solution. So I've got my gloves on to make sure that I'm keeping my skin safe. So we're going to put some of this hydrogen peroxide in here. And then we want to make sure that that gets mixed up very well. So we're going to suspend the hydrogen peroxide. It's not really dissolving, right? We're suspending it up and making really big droplets of it. so that it will be ready to react. So now I'm going to turn off the lights so that we can see this reaction happen better. So here you can see, after I warmed up the solutions a little bit to get everything dissolved and mixed together, both of these solutions are now glowing quite brightly of their own accord. So what's happening? We have a very energetic chemical reaction happening. Whenever we put these particular materials together, the peroxide actually has a lot of energy stored in it. So whenever it releases that energy, it can give that energy into other forms. So what's happening here is the peroxide is reacting with one compound in there, and then it's making a compound that has a very high energy. That compound actually falls apart spontaneously into two carbon dioxide molecules. But those two carbon dioxide molecules are extremely energetic. And when they fall apart, they will bump into the other molecule that's in solution that's known as the dye molecule or the fluorescing molecule. And that fluorescing molecule will then absorb the energy from the very energetic carbon dioxide, and that will put it into a high energy state. And then when it drops from that high energy state back down to a lower energy state, that's when it gives off the light. So the reaction that's happening in these two is actually the same. So we're using peroxide in both cases, and we're making that very energetic molecule. The difference that gives us the two different colors is that we have different dye molecules in these two solutions. Chemical reactions happen at different speeds at different temperatures. And so, if we heat these solutions up, then we should see them glowing brighter. As you can see in this time-lapse video, as the reaction warms up, it gets brighter.
So that's our chemiluminescence reaction.